Hello everyone, I'm Shubham Vani with my teammates Lin Feng Li and Yang Liu. We'll be presenting about parking assist, that is basically path planning with the enhancement of informed RRT. So currently a lot of companies are working on transitioning from L2 level autonomy to L3 level autonomy. So if the car is in a constrained situation such as a parking lot or around tight corners, some cars do struggle. And also with the parallel parking problem, if we do know the map of the parking lot, we could actually use RRTs to uh, reach the position that we want to. What we are trying to implement is informed RRT to the non-holonomic systems with the enhancement of goal sampling, and to benchmark these different algorithms for the distance that it takes and the time and the number of nodes, that is the memory that it has to take care of. So the first case is plain RRT with no goal bias. The second case is RRT with a dense sampling at the goal, which implies that once the uh, RRT is in the neighborhood of the goal, it samples densely at the same location, which my teammate which my teammate Lin Feng will be covering. The case three is the same thing, but with the enhancement of point duration within ellipsis. That is, this is the informed RRT part where once we know one of the paths, we generate new points within the same ellipse to get more optimal solutions. So, looking at the problem, essentially we are using we are using car kinematics which have been shown in the differential equations in the top right corner. uh, we use a linear array for different velocities, for different steering angles, and for different times, and the potential positions that a car can be given that it started in a particular x, y, and theta are shown in these motion primitives here. We get these by solving simple differential equations using the Euler method, and we generate these motion primitives. One interesting thing is that we are also incorporating obstacle avoidance, such that if the motion primitive is growing into an obstacle, we don't let it grow into an obstacle by just moving on to the next loop. And as we all know, an RRT keeps on expanding. It generates a random point. It finds the closest point in the node in the entire graph structure, and then it grows from that closest node to the random node that we have to the random node that we had found out. And thus we can see that in about 10 seconds, this RRT, vanilla RRT, is able to find a solution in the threshold of the goal structure.
For this part of our project, I implemented parallel parking assistant based on our RT with non-holonomic system program. The first step is to define the map and also car modeling. The first picture here on the left is the map, and there are some obstacles which come up with a parking spot in the middle, and this can be used in our parallel parking. And the picture on the middle shows how the program looks like. And if we zoom in a little bit, we can see that the car trace is shown here, where this is a parking spot and the red box is the car. And the checking condition is that the four wheels coordinates need all be inside the parking spot. And the other part is the how I did the modeling of the car. I used the realistic car dimension where the car length is about 2.5 times of the car width. And the picture are from online, which shows the math of the calculation of the four wheels coordinates. The calculation based on the coordinates of the center of the car, which is this point here, and also the car length, car width, and also the car angle. The car angle is basically the theta here, which is different from phi, which is the steering angle. And I used some way to optimize the parking sampling model. When the car is far from the goal, the main idea is to drive toward the goal. But when the car is close to the parking spot, it switches to parking mode. And when it's in parking mode, it needs more accuracy and sensitivity because the car needs to be accurately inside the parking spot. So based on this idea, when near the parking spot, I set a smaller step size for velocity and angle when we do the motion primitives. And the motion primitives picture is shown down here, and where we can see that if we have a smaller step size for both of the velocity and angle, the edge can be much more smooth and accurate. And also near the parking spot, the steering angle are allowed to be negative, which means reverse driving in real life. And the steering angle range is said to be larger because when we're parking, we probably require more steering. And another important optimization is to let the bias be big whenever a node is near the parking area. That means when the car get close to this area, half of the random points of our RT are chosen to be the goal location. And we continue to the RT to find more paths within the parking region. So that basically means that whenever the car reaches this circle, the car will not easily get out because we want the car to stay in this center whenever it arrives, and then increase the sampling frequency and sensitivity within the parking spot. And here's a picture of our final results of the parking assistant, where the black line is the path of the car, and the red box is a car where we can see that four wheels are all inside the parking spot. And here's a video that shows basically how it looks like. And the number of nodes generated is about 1700, which means that there are a total number of 700 nodes generated. This is not a small number, so the program actually cannot run very fast. And this is another example where we can see there is a reverse driving. The car drive here and go back and then back again, and the car is finally within the parking spot. And this is a real-time screen recording of how the nodes are generated and how the paths are plotted, but this is speed up 4 times. So this is for the parking.
In the previous slides, we have discussed how parking assist is implemented using RT. However, RT does not always converge successfully and is not asymptotically optimal because the existing state graph biases future expansion. For RT star, it improves the convergence rate, but takes a lot of time to find the final solution. Here, we introduce our solution to improve the convergence rate and the final solution quality, informed RT, inspired by informed RT star. Before we go into details of informed RT, let's take a look at the three GIFs of RT star, and informed RT star. As you can see from the GIFs, informed RT star outperforms RT and RT star in rate of convergence, final solution cost, and the ability to find difficult passages. Similar to informed RT star, our informed RT differs from RT and in RT star in that once the solution is found, it focuses the search on the part of the problem that can improve the solution. It does this through direct sampling of ellipsoidal heuristic. The heuristic sampling domain is an ellipse with the initial state x start and the goal state x goal at focal points. The shape of the ellipse depends on both the initial and the goal states, the theoretical minimum cost between the two, C minimum, and the cost of the best solution found to date, C best. The eccentric of the ellipse is given by C minimum over C best. In the image on the right, the start and goal states are shown as green and red respectively and are 100 units apart. The current solution is highlighted in magenta, and the ellipsoidal sampling domain is shown as a gray dashed line for illustration. Improving the solution decreases the size of sampling domain, creating a feedback effect that converges to within machine zero of the theoretical minimum. To conclude, this project introduces a new path planning algorithm, informed RT, developed by referring to the existing algorithms. We think that this new algorithm will benefit and inspire others. We have also integrated the non-holonomic system with our algorithm, bringing path planning to another level in real life. In the future, we would still love to try out different algorithms with non-holonomic systems, such as inform RT start, and compare which one works the best with it. We also want to explore techniques to focus the search without requiring an initial solution. And that's it for our final project presentation. Thank you so much.